Greetings and salutations. In this topic we are going to look at the motion of satellites as an extension of uniform circular motion. In the previous topic it was the application of contact forces which provided the centripetal force and the centripetal acceleration. For satellites, the required centripetal force is going to be provided by Newton's law of universal gravitation. I have listed a number of relevant videos in the comments section below. In particular, the motion of satellites as they go around the Earth and compared to an object that is falling through the centre of the Earth is a very interesting one. Newton's law of universal gravitation simply says that there is a mutually attractive force between two particles. The magnitude of this force can be determined using two proportionalities. This magnitude is directly proportional to the product of the two masses, and inversely proportional to the distance between the centre of the masses. The two proportionalities can be combined into one. To solve problems, we need to introduce the idea of Newton's universal gravitational constant. To calculate the value of gravity on any planet or moon, we can equate Newton's law of universal gravitation with his second law of motion. This question requires us to use Newton's law of universal gravitation to determine the magnitude of the ratio. The first step is to write down Newton's law of universal gravitation for both the Earth and for the Sun. I have also included the mass of the Moon, the mass of the Sun and the mass of the Earth for future reference. I can now substitute the formulae into the ratio. Both the constant and the mass of the Moon are common to both, therefore we can cancel them out. If we rewrite our equations, they now only involve the mass of the Earth and the mass of the Sun, and the radius of the Earth to the Moon and the radius to the Sun. Okay, and notice that both the radii are squared. Now I'm going to plug in the values for our ratio, including the values for the radii. When you evaluate both parts of the ratio, we get a final answer of 0.455. We're now going to look at the motion of satellites in circular orbits. A satellite in an orbit can be any form of technology, or it can include things like the Moon orbiting the Earth, or planets orbiting the Sun. For calculations, we need to measure the time for one orbit. This is called the period, and is represented by the symbol capital T. And to calculate the speed of our satellite, we need to measure the circumference of the orbit. Similar to the motion around banked curves, the motion of satellites is dependent upon the radius of the orbit and not on the mass. Using Newton's law for universal gravitation and our formula for calculating centripetal force, we can derive the formula as highlighted here, where g is the universal gravitational constant and m is the mass at the centre of rotation. Usually it's going to be the planet Earth. It is important to remember that when using these equations to solve problems, that r is measured from the centre of our mass to the satellite, and that this is different if we are calculating the height above the Earth's surface. This formula derivation comes straight from the curriculum outline. To start this question, I'm going to write down the centripetal force equation and the equation for Newton's law of universal gravitation. I've also included the description of the units I will be using. Since the centripetal force has been provided by the gravitational force, I've equated the two equations. By cancelling out common factors on both sides of the equation, what we are left with is that v squared is equal to gm on r, where m is the mass of the Earth. To complete the question, all we need to do is take the square root of both sides of the equation. We can use our equation from above to calculate the speed of a satellite in a geostationary orbit. The first step is to substitute in the values that are provided in the question, with a calculated value of 3.09 times 10 to the 3 meters per second. To complete the topic, we're going to look at two types of satellites: weather satellites and communication satellites. It is important to be able to explain why the centre of rotation of the circular orbits must coincide with the centre of the Earth. It is important to be able to differentiate between low-altitude equatorial orbits and low-altitude polar orbits, and to be able to explain their uses in meteorology and surveillance. Communication satellites, however, have a geostationary orbit. This is important because it means that its period of rotation, or its orbit, is 24 hours. So the effect is that it is also going to have a very large radius relative to the other types of satellites, and must rotate in the Earth's equatorial plane and in the same direction as the Earth rotates. To complete the topic, I have chosen some past exam questions which we can use to demonstrate the highlighted properties of the satellites. To answer this question, we must first understand what a geostationary orbit is. So a geostationary satellite appears to be stationary above the Earth. So its period of rotation is going to be 24 hours, and the direction of orbit must match that of the Earth's rotation, which is from west to east. One advantage of launching your satellites in a west to east direction is that they will already have speed due to the Earth's rotation, and to place it in a west to easterly orbit will require less energy or fuel to be used. The photo on the left has come from the QuickBird satellite. It is orbiting at a height of 482 kilometers above the Earth's surface and has a mass of 950 kilograms. The International Space Station on the right has an altitude of 390 kilometers, but it has a mass of 420,000 kilograms. To determine whether the QuickBird satellite is faster or slower than the International Space Station, we can look at our formula V is equal to the square root of gm on r. Therefore, since the altitude of the QuickBird satellite is more than the altitude of the International Space Station, its speed is going to be slower. The different masses of the satellites are not going to affect the speeds of the satellites, because the speed is dependent on the mass of the Earth, not the mass of the satellite. And finally, one advantage of the QuickBird satellite is that being at a lower altitude, it's going to have greater resolution in its photos.